Welcome. Hello everyone. Today we are covering Unit 2, Lesson 6, Evidence for Evolution 1. Our objectives today, we are going to describe how evidence from comparative embryology supports the idea of evolution. 2, we're going to describe how evidence from homology supports the idea of evolution. We're going to describe how evidence from vestigial structures supports the idea of evolution. And number 4, we're going to discuss the evidence that evolution has occurred and is occurring on Earth. And this is in our state standards for evolution. Evolution is 25% of your state test. All right, so our first little activity, we have 2 skulls here, and one is the saber-toothed cat. It was a fearsome predator that first appeared about 55.8 million years ago and existed in North and South America until about 11,700 years ago. The skull of the modern-day lion and an Ice Age saber-toothed cat have many anatomical similarities. These similarities suggest that the 2 animals had a common ancestor, although they are not directly related. Okay, this is the saber-toothed cat from the Ice Age. Right, you can see the big teeth. And this is a lion. Okay, so look at these 2 skulls and note some of the similarities as you compare the 2 skulls. Okay, you can pause if you want to look for a couple of seconds, and then I'll give you some examples here. All right, so the fangs. Both these skulls have long upper fangs, although, like as we pointed out, that saber-toothed cat has much larger and longer. Their forehead. They both have a low, sloping forehead. So here's the forehead. Here's the forehead. You can see the similarities. Eye socket. Both have similar eye socket. Eye socket, eye socket. They're both forward facing. The jaw. Both have a long jaw equipped with fangs and front and back teeth. And look in the jaw and the teeth, and you can see similar pattern of teeth. Masteric fossa, and that is noted here if you weren't sure of that structure. And this, right, mastication is chewing. Okay, so this is a connection point for that large muscle that controls the jaw. Okay, so they have strong jaw, strong muscle controlling that jaw. And then finally the sagittal crest, and that's the little point here at the back. Both have a pronounced sagittal crest, again having to do with muscle attachment. Okay, so several lines of evidence from anatomy and development support the theory of evolution. Okay, at first glance, you might think that whales and sharks, right, they look kind of similar, they have the same habitat, they might be closely related. But if we conduct further observations, we are going to find some very important differences, one of which is that sharks have gills for breathing, while whales have lungs, so sharks can breathe water. Well, they can breathe the oxygen in the water, where whales need to extract oxygen from air. So scientific evidence indicates that whales evolved from air-breathing mammals that lived on land. A whale's lung is a structure that shows its shared ancestry with other mammals, other air-breathing organisms. Okay, so if we look closer and look more specifically at those structures, we can better determine ancestry and closer ancestors. Okay, so scientific evidence to support the theory of evolution by natural selection using physical characteristics. So one such line of evidence is the observation that many species have similar physical characteristics. And the three main lines of evidence to support this are anatomical similarities. Okay, so these are organisms that have similar anatomical features, such as limbs and number of limbs. Right? Many organisms have 2 front limbs, 2 back limbs, 4 total. Okay, that suggests they have a common ancestor. Embryonic development. Some features become apparent as an embryo develops. And we're going to look at comparing embryos from different species and at different stages, how they are similar and how they are different. And that can be evidence of evolution. Vestigial structures. Some features that had a function in an organism's ancestor, but no longer have a function. So there are features in organisms that they don't use, and the reason that they have them is because there was an ancestor that did have a use for those structures. Okay, so first let's start with that comparative anatomy. Okay, so we're comparing the anatomy of different organisms to determine similarities or differences. Okay, and we're going to look at a chicken and an elephant. Okay, they don't seem very similar at all. We would say they are completely different. But if we look at them in a biological sense, like a biologist would, we're going to see that they are more similar than you would think. They have many shared structures. We call those homologous structures. Okay. These are structures in different species, but they are similar enough to suggest that the species had a common ancestor. Okay, so one of the ways we can look at an elephant and a chicken is at their skeletons. All right. And if we ignore the size difference, so you can see we have the chicken more similar size to the elephant, so it's easier to compare where we eliminate the size difference. And look at this whole list, and there's more. This is just a few examples of structures that are homologous. Okay. They may be a different size, a different length, but they still have that same pattern. One that I find really fascinating, and we'll look at this a little bit more, are phalanges, and it's one of my favorite words, phalanges. These are our digits, our fingers and our toes. And while the foot of a chicken and that of an elephant are very different, if we look at that pattern of bones, we will see similarities. They'll have the same numbers, the same groupings as each other. And there's many organisms that have these same patterns in the phalanges. And then same thing with our front limbs. While the bird's front limb is a wing, we can see that we have the same numbers and patterns of bones, even though they're different lengths and shapes and end up doing different jobs. But they're both for movement. We can see similarities. Like here, they both have a humerus bone. Okay. Here's some other examples of homologous bones. Okay, these are types of homologous structures. And we're comparing a penguin, an alligator, a bat, and a human. And you can see the color coding that shows these homologous. Again, the phalanges are the digits, the fingers. And you can see here yellow is the phalanges. Even a bat whose front limb is a wing has that similar pattern of phalange bones. The penguin as well, an alligator, and the human. All the way through that front limb. You can see those homologous bones. They're different shapes and different lengths. They end up doing different jobs, but we have that same pattern. So many mammals have similar skeletons. This is evidence to suggest that they shared a common ancestor. And looking at skeletons helps to relate organisms to one another. Okay, so we're going to be looking at some skeletons on the next few slides and finding similarities in the skeletons. Okay, here they are. This is also in your content if you would like to look at it from that aspect. So we have a bat. This is a hare, a bunny. This is the domestic cat. This one is a mole. I found this one a little bit difficult to see the bones, and the guinea pig as well. They're just a little small on here. But like I said, you can check it out in your content, and it does allow you to zoom in a little bit. And we're looking for homologous structures, so homologous bones specifically. So you can pause it here. The next few slides are going to show you some examples and there's more than the examples. Okay, so pause and then you can restart. All right, first example, humerus. So in the red, you can see the humerus that is homologous. Like I said, the mole is a little difficult to see. They also showed us the radius. The radius in all these organisms. And this is paired with the radius would be the ulna. The ulna. Okay. If you take anatomy and physiology, you'll learn more about all these bones and identifying them as well. It can be fun if you like that. Me, I'm not so good at memorizing, but I still had fun in my anatomy class. All right. So similarity in homologous structures implies that the underlying structure arose in a common ancestor and became modified as different populations adapted to different environments. Okay. Horses were one of the first that we had discovered all those intermediary steps through the evolution of the horse, and we can see how those structures became modified to adapt to their environment. Okay, so this is descent with modification in the horse. Okay. Here's that comparative embryology, and we can look at these very different species, the fish, salamander, tortoise, chicken, human. Right at the bottom are older, the older embryo or fetus, we call it. But if we go back to the early embryo, you can see that they are much more similar. Okay, before they differentiated. They all have gill slits, they all have a tail. And it's hard to distinguish which is which species until it develops further. And this, again, is evidence of evolution. Okay, next we have vestigial structures. These are structures in organisms that have no function. Like the ostrich, the emu, these are flightless birds. They still have wings, but they do not fly. But their ancestors did. So that is why they maintain those wings. Humans have vestigial structures, goosebumps for our ancestors that had fur to help keep them warm. Our appendix, we're still unsure exactly of the function of our appendix, but we think a previous ancestor ate more plants, needed more digestion. Again, wisdom teeth, same thing. They needed more of that grinding teeth. And then finally the tailbone. And we're going to talk about the tailbone here quickly. We have a tailbone. What do you think is the reason? Where do you think this tailbone came from? And you can stop and think of your explanation, and we can discuss that in class. Here is our summary. And finally, there is a quiz for today. 2.06, 3 questions. Have a great day, everyone. Bye.